Okay, well, so this is already final lecture in my series, but there will be more beautiful lectures to come during the week. So let me sort of try and slowly move to representation growth, but keep a little bit an eye on subgroup growth just to sort of make the connection to yesterday. So yesterday we more or less ended up with subgroup growth theorem, polynomial subgroup growth theorem, which somehow said that if gamma is a finitely generated residually finite group, so residually finite was a kind of technical term that makes sense when we explore subgroup growth, then the following is true. So gamma has polynomial subgroup growth, and therefore we can sort of study its subgroup zeta function if and only if, and there was an algebraic characterization, if and only if gamma is virtually, so up to finite index, soluble. And there was an extra condition, so we saw that this lamplighter group did not have kind of polynomial subgroup growth, so it's virtually soluble of finite rank, so finite prüfer rank. And I will now sort of drop the prüfer, and the rank will for me always mean kind of this kind of rank, and that was the basically the minimum exists. There's a natural number R such that if you have a finitely generated subgroup of gamma delta, then it can always be generated by at most R elements. That was this notion of prüfer rank, some kind of finiteness condition. And that was kind of a difficult result. I sort of hinted a little bit at what might go into the proof, but there's a kind of elementary version, I mean a kind of local version. So the theme about these kind of subgroup zeta functions was a bit that you could reduce things to local zeta functions. And so there's also a local version of this. So this is the kind of local, like the kind of local pro P version. And that is my excuse for kind of starting to talk about p-adic analytic groups. So if you have a pro P group, G is a finitely generated pro P group. So that means G is a finitely generated pro P group. So pro P group means you're a profinite group. And I told you already that sort of one way to get profinite groups is to produce kind of the profinite completion of something. So this was a topological group that you get by stringing together all kinds of finite quotients of an abstract group. And this group, so I didn't explain this, but this group basically embeds as a closed subgroup, closed topological subgroup, into the Cartesian product of all these finite groups. So each of these finite groups you equip with discrete topology. And so because it's finite, it becomes a compact kind of group, totally disconnected. And so this big Cartesian product with the Tychonoff topology kind of becomes a compact, totally disconnected topological group. The group multiplication and the inverse map are continuous. And then you somehow string these things together, so you impose some compatibility condition coming from the kind of structure within gamma. So if you have nested kind of nested normal subgroups of finite index, there's a natural map from gamma modulo delta 2 onto gamma modulo delta 1. And that gives you some kind of compatibility condition, which is a closed condition, which means that you get a subset where these kind of, if you think of these entries as coordinates, where the coordinates satisfy some kind of compatibility conditions coming from this kind of nesting of normal subgroups. And that produces then this kind of closed topological subgroup here. So that was our example of a kind of profinite group. And an arbitrary profinite group is just a compact, totally disconnected topological group. And you can always picture them as closed subgroups in some Cartesian product of some arbitrary finite groups with the kind of imposed Tychonoff topology. Okay, so profinite groups are nothing else but closed subgroups of Cartesian products of finite groups. Okay, and these groups turn out to be very interesting. I mean, they appear in Galois theory, sort of, if you have infinite Galois extensions. But for many other reasons, these are interesting groups. And they kind of form a kind of counterpart to the kind of, the more commonly kind of studied kind of Archimedean Lie groups or other groups of that type. And a pro P group, well, it turns out that these profinite groups, just like finite groups, they have a Sylow theory. So every every finite group has Sylow P subgroups, and so every profinite group has Sylow pro P subgroups. And they are nothing else but kind of closed subgroups of Cartesian products of finite P groups. Okay, and so it's a very interesting class of kind of groups. These are kind of the local things that we get, and the most basic example is, well, if you take SLN ZP, where ZP denotes the p-adic integers, this will be kind of a profinite group. It will be the inverse limit of the congruence kind of quotients, the finite congruence quotients, when you mod out some power p to the k. And it's not quite a pro-p group, but if you move down to the first principal congruence subgroup, then you are a pro-p group. So it's virtually a pro-p group. So these are examples of the kind of groups that I'm talking about. Okay, so in the finite degenerate pro-p group has polynomial subgroup growth. So G finite, then G has polynomial subgroup growth, where you should only count kind of closed subgroups of finite index, but they turn out to be the same as abstract. So every abstract subgroup of finite index will be closed automatically. This is a little theorem, but I mean, in principle now, all these things we're doing should be kind of in the topological world. We're doing our topological groups, so we should be counting closed subgroups rather than arbitrary subgroups. But anyway, in this setting, it's the same. So G has polynomial subgroup growth if and only if G is p-adic analytic. So if and only if G is p-adic analytic. So it has a manifold structure over the p-adic numbers and with an atlas, and the group multiplication is just continuous. It's given by some kind of formal power series. So it's kind of analytic. But this allows for an algebraic description, which is very useful for this. So this means, and this is my connection here to the rank. So this just means that the rank is finite. So this means that this is a group of finite rank. Now in the topological sense, so that means that the supremum of all the minimal numbers of generators H, as H runs through all closed subgroups of G. And this is, again, generators in a topological sense. So these are always kind of uncountable groups if they're not finite. So you cannot generate them by finitely made elements in the abstract when, so you take the closure, the topological closure of whatever these elements generate in the abstract sense. And so this rank is finite. So this turns out to be equivalent to the group being p-adic analytic. So this is kind of the algebraic way of describing that. And you see there's a connection. I mean, these two things kind of come together. And there's another kind of more down-to-earth kind of description of what this means, which is maybe reassuring if you meet this for the first time. So it means that G embeds, so there exists some natural number n such that G embeds as a closed subgroup, so let me denote it by this, into SLNZP. So they're just, so unlike in the world of real Lie groups, here every closed subgroup of, well, this is a prototype of a kind of a compact p-adic analytic group. So every closed subgroup is automatically analytic. So it's a bit different from what we know from the kind of Archimedean world. So this is a large class of groups. That's what I'm trying to say. So yeah, it's just basically all kinds of pro-p groups that are linear over QP. Okay, so this is not too difficult to prove. So this I could expose if I had another lecture or something, or another 10 minutes, but I will sort of refrain from doing that. It's very easy to see that when you have finite rank in this situation, that you have polynomial subgroup growth. So the direction from if you take this as your if you take this as your starting point, then it's very easy to see that such groups always have polynomial subgroup growth, and the other way around is a bit more complicated. And the equivalence of these kind of things is more difficult. The equivalence of this condition with p-adic analytic or this is more difficult. Okay, so we have that. And if anybody wants to know how to do it, you can ask me later. So embarrassing thing is, slightly embarrassing thing is, lack of knowledge. So we don't know much about the subgroup growth. So let's put open. I mean, we're counting sort of open subgroup growth of groups such as SLNZP, only in the case n equals 2, we know everything, but somehow for n greater or equal to 3, we know hardly anything. And this is very embarrassing because somehow these are very nice groups. I mean, unlike this world of nilpotent groups where somehow we expect to be complications all over the place because there's so many different kind of nilpotent groups. I mean, these are very special groups, right? So we should be able to say something. We don't. I mean, we don't know. So we don't know much about that. Okay, so there's lots of room for people to get involved. The reason why it is sort of nice or useful to have this kind of analyticity is because now we can apply Lie theoretic methods, and that is something that I want to use also in the situation of representation growth. And so it's worth to maybe start this picture here. So if I have one of these, compact periodic analytic groups, so think about SLNZP, and that is not quite yet a pro-P group, and not every sort of periodic analytic pro-P group has a nice Lie theory, but there's always an open subgroup, so this is one of the parts of this kind of theory. In our case, we can take SLN1, this first principal congruent subgroup, the kernel of the map onto the natural map onto the finite group of Lie type SLNFP, which happens to be, the technical term is uniformly powerful. So I'm not going to define what that means, but you can ask me later if you want. So this is a uniformly powerful pro-P group, subgroup. Sitting there, it's an open subgroup, so it's sitting there as a subgroup of finite index. And this group has a nice kind of Lie correspondence, namely their kind of their logarithm and exponential maps to a corresponding ZP Lie lattice. So there's a powerful ZP Lie lattice. And somehow, in good situations, not only at this level you get this correspondence, but all the things, like if you imagine you replace G by U, all the kind of subgroups you care for, they kind of correspond to Lie sublattices on this side. So that means that sort of, and it's index preserving. So somehow that means that rather than counting subgroups in the group world, you can count ZP Lie sublattices in that world and recover your sort of subgroup growth. And that's a very useful thing to have because somehow this then becomes much easier to translate into periodic integrals and kind of prove things about that. And let me just sort of indicate how this comes about. How do you get a Lie lattice suddenly associated to such a group? So it's a limit process. What you have to do, so you take as an underlying set, you take the group itself, and you define new operations. Addition, you need addition in a Lie lattice, and you need sort of the Lie bracket. And you also need multiplication by ZP, but that sort of comes about when we do addition kind of. And so how do you add two elements? So if you take X and Y now in U, and you want to define a new operation plus, what you do is you send these elements down into the group. So if you take, it's a pro-P group, so if you take high powers of P, then you move down in the group. And then you multiply them as if, you multiply them down here. And then the special feature about these groups is that you can extract also P to the nth roots. So you can then extract P to the nth roots. So that, and you take the limit, so you take the limit as n goes to infinity. And so that turns out to give a commutative kind of operation within your group, sort of mimicked within your group, which gives you the addition that you need sort of in this Lie lattice. And you do the same thing essentially for the Lie bracket. So if you want to do the Lie bracket, you do another limit of that kind. You take the group elements that you get by pushing them down in the group. You take the group commutator, and then in this case, you have to extract the p to the 2nth root. Okay, and again, there's some kind of limit like that. So there's an intrinsic way how you can move from your group to this kind of Lie lattice, and there's another way to go back via kind of the Hausdorff series. Okay, but for us, this is all very technical. For us, the main thing is that in good situations, kind of these sides kind of talk to one another, and you actually get an isomorphism of categories. Okay, and so the relevant result in this regard is the following theorem. So let me just mention this as an example for several results of this kind. So this is a theorem of Gonzalez and myself from 2009. So it says that, I mean, how would you discover that something maybe has a nice Lie theory or something? So it's sufficient, for instance, the following. So if G is torsion-free, so for this Lie corresponds to work, you have to be in particular torsion-free. This is kind of a must, because otherwise you're not going to get a ZP lattice. So if you're torsion-free, p-adic analytic, and the dimension, so pro-P group, p-adic analytic pro-P group, of dimension. So these come with an analytic dimension, and this analytic dimension, I mean, if that is less than P, then you have a nice Lie correspondence. So let me just put it like that. So then G admits. It's not going to be uniformly powerful, but it's going to be a slightly more technical thing, but it admits a kind of nice Lie theory in that sense. That we can do subgroup growth or whatever we want to do on the Lie theory side. So the technical term is it's a p-saturable kind of pro-P group in the sense of Lazare. Okay, and so that is relevant if we're interested in things like SLN. So the dimension of this is, of course, n squared minus 1. Yeah, so we may have to throw away some primes, but we can sort of use these techniques for all primes that are larger than n squared minus 1. Okay, and maybe we have to work a little bit harder for small primes. So the dimension, in this analytic dimension also has a meaning in this kind of algebraic description. So the dimension of G, the analytic dimension of G, it's nothing else but the dimension of U, of course, because it's an open subgroup. But the dimension of U is nothing else but the rank of U, and it happens to be actually the minimal number of generators of U. It's independent of your choice of U. And it's the same as the ZP dimension, then, of course, of your Lie lattice U on this side. Okay. So the dimension sort of is not the dimension is also something we can talk about in algebraic terms, and kind of we don't need the analytic machinery for that. Okay. If all this is very strange, there's of course also a big Lie algebra kind of sitting in this. So there's a big Lie algebra. So the Lie algebra associated to G is just when you move from this Lie lattice, then you lose information a bit, but you move from this Lie lattice to a QP Lie algebra. I mean, that's the Lie algebra, and again, the dimension of this is the dimension. Okay, so now I want to take this as an excuse to move towards the representation growth. And well, the basic setup is very similar to what we did for subgroup growth, but we're going to study rather different groups, namely groups more of this kind now, rather than kind of nilpotent groups. And so you will see that in a moment. So here's the kind of basic definitions or jargon for representation growth. So instead of enumerating, so now I'm switching to a general group gamma, but okay, I will not write everything twice. So you can either be an abstract group gamma, or you can be a profinite group G. And the definitions are the same, except that in one case you only consider continuous kind of representations. So gamma is now a group, I mean, whenever this makes sense. And Rn of gamma is just the number of, so we're interested in the number of irreducible representations, and we want them to be n-dimensional. So finite dimensional of a given dimension n, dimensional, and we want to take representations over the complex numbers, so ordinary representations, complex representations of gamma up to equivalence, up to equivalence. And okay, that in general, of course, this could be an infinite number. Of course, in that case, we don't have nothing, and we don't get an algebraic sequence. So we're interested in the case where this sequence of numbers is actually an arithmetic sequence of finite kind of natural numbers. And so the technical term is kind of, so is that the group is representation rigid. So gamma is called rigid. Rigid, this is kind of the term used by definition if these numbers are finite. And in that case, when we are rigid, then of course we introduce this kind of zeta function. And I will now drop this. I wrote, so to distinguish it from subgroup zeta function, one can write things here, but I will, from now on, I will only talk about representation zeta function, so I will not put any kind of qualifier here, but I mean, there could be a qualifier here. So, so this is, as you would expect, the Dirichlet generating series n equals 1 to infinity, r sub n of gamma n to the minus s. And again, we're interested in, so this will again maybe have polynomial or not polynomial growth. So we're interested in polynomial representation growth. And if we have polynomial representation growth, we're interested in this kind of abscissa of convergence. So then this will actually converge for real part of s greater than alpha of gamma. And again, I will not put a qualifier there. So now everything is representation, kind of zeta functions, representation growth. So we play the same match in some sense now in a slightly different context, namely, rather than looking at subgroups, we're looking at n-dimensional irreducible representations. Okay, and there's a very basic observation. I mean, abelian groups are no good now, right? So if we want to look at examples, the idea might be, okay, let's look at abelian groups first because we understand them, but all the representations are one dimensional. So if I'm an infinite abelian group, then this will explode in my face, right? So somehow there's a condition, there's an easy condition. So here's an observation or lemma. So if gamma is rigid, then a necessary condition is that gamma has a condition called fab, so it has finite abelianizations on finite index subgroups. So this means whenever you take the finite index subgroup of gamma, then the abelianization of delta should be finite. It's finite. So it's not a perfect group, but it looks a bit like a perfect group. It's like kind of, and it's kind of virtually hereditarily perfect in some sense. Hereditarily virtually perfect, I don't know, something like that. And that's just, otherwise we will certainly sort of blow up these kind of numbers too far. So we should move away from abelian, nilpotent, all these kind of groups that we looked at before, and rather we should turn to groups like SLN or something like that. Okay, so we're playing in a different field now. And, and okay, why should all of this be interesting? So there were some kind of pioneers in the subject, of course. So one of the pioneers was André Heiken. And so he produced a wonderful example. So this kind of example. So he proved other important things, but this is kind of a hands-on example. I can start here rein. And I think this is it 2006? Somebody know? Anyway, I think it's 2006. So it's also some time ago. This somehow, yeah, 2006, I think. So he proved the following rather general results. So if you take any complete discrete variation ring, so complete discrete variation ring R with maximal ideal M. So think p-adic integers and the valuation ideal generated by P, or think characteristic, positive characteristic, think positive power series over the field with P or Q elements. Okay, let's say Q elements, and the ideal generated by T. So it's surprising that this works algebraically no matter whether you're in zero characteristic or in positive characteristic. This is something that we don't know how to do in general, but in this example, it works. So then you can actually compute, or he computes the representation zeta functions for SL2 over this ring R. And it's, the answer is kind of short enough so that I can actually write it down, and it sort of also illustrates a few points that I want to make. So first of all, you have, so this is a complete discrete valuation ring with residue field R modulo M. So it's a finite residue field with finite residue field FQ, the finite field with Q elements. Then, of course, you see all the representations. You have a map from this group onto SL2FQ, so you see all these representations of this finite group of Lie type, and it's a whole theory of itself to sort of work out things like that, right? So this is kind of Deligne-Lustig theory. This is kind of elaborate kind of machinery to produce these kind of representations and handle them. But that can be done. And then there's a kind of thing that looks more like the kind of things that we've seen before. So there's a rational function q to the minus s. And let me write like that. So in the denominator, 1 minus q to the 1 minus s. And in the numerator, you see a sum of 3 terms, and they look a bit like this. So 4q times q squared minus 1 halves to the minus s. And there are 2 more terms like that. They're not important what they are. They look exactly like that, a little bit different. So what is important to observe in this situation is that here, where I haven't spelled this, one could write this down explicitly, but there's also maybe a sum of 4 or 5 terms. This is not a rational function in q to the minus s. Yeah, you see here, there's a term q squared minus 1 halves to the minus s. So unlike in the subgroup growth situation, this is a slightly different kind of thing. And the reason is that this is not a pro-p group. Yeah, so we have this thing. I mean, this is not a pro-p group. We have this finite quotient on the top. So if I was to go down to the pro-p group, then again, I would get something that is sort of maybe not. It would be something in p to the minus s. Then all the irreducible representations would have dimensions at powers of p. But because we are not doing this for good reasons, we see this kind of mixed type of rationale in things. But the thing that sort of crops up infinitely often is kind of powers of q. If you expand this as a geometric series, then you get sort of finitely many of these terms multiplied by something that is actually a power series in q to the minus s. Okay, so it's a slight generalization, but it's very close to what we had before. Okay, and this is just by character theory. You can, I mean, okay, you have to do it. It's not easy, but this is like maybe 2 or 3 pages character theory. Character triples is the kind of technique that you use. And yeah, we don't know how to generalize this kind of thing. I mean, in that explicit kind of form to higher dimensional groups, but there's a theory that says something about them. In particular, the alpha here is 1. Yeah, so the pole that you see here, the alpha is 1. So in this case, alpha of SL2R is equal to 1 in particular. Okay. So another thing that I'm not going to write down, but which is probably reassuring, is that unlike the situation with subgroup growth, here this alpha, I mean, when you have polynomial representation growth, this alpha is really an invariant of the commensurability class. So you can move up and down by finite index. Yes, please. Q is odd, yes, you're right. I'm brushing a few things under the carpet. Q is odd. So this thing Q is odd. So this is so in characteristic 2, because we're looking at SL2, things are slightly different. So Q is odd. Thank you. So apart from maybe being interested in in these finite groups of Lie type, or these kind of simple kind of, simple in inverted commata, simple compact p-adic compact p-adic analytic groups, why would we care about these things? Where's the Euler product? And so there's an Euler product. So this kind of gives information if you feed it back to the representation growth of arithmetic groups. And these are a well-studied class of groups. So there's a theorem. So this feeds back. It's back into the representation growth or zeta function type of, let me just say, kind of semi-simple arithmetic lattices. In characteristic 0. So e.g. groups like SLN over the integers, Z. So these are very well studied groups. We're very much interested in the representation theory of such arithmetic groups. And so, well, maybe we cannot classify all the representations, but we can sort of at least count them. And so there's this kind of theorem. So again, maybe this is like with the Q odd. I'm not going to be very precise here. So this is kind of, the statement is kind of, maybe there's some extra technical assumptions that I will sort of, that will not discuss, but the theorem of Larsen and Lubotsky. And I think this is 2008, is that possible? Oh, yeah, I think, yeah. So if you take one of these groups, so in general, you will have some kind of, simply connected, absolutely simple kind of algebraic group. So there will be some condition G, so think SLN, G equal SLN. And you can not only do this for the rational integers, you can do this for the ring of integers in some number field. And you can also invert some primes. So there's a whole kind of general kind of setup where you have a big family of these kind of semi-simple arithmetic lattices, irreducible kind of lattices. And then if this has what is called the congruent subgroup property, so somehow there are two topologies naturally sitting on such a group. One is the profinite topology. So this is a linear, infinite joint linear group. It is residually finite. And there's a profinite topology given by finite index subgroups. But there's also a kind of congruence topology given by the ideals. I mean, they're all a finite index in this ring of integers, or this S ring, this ring of S integers. And so you get another kind of finite topology. I mean, well, not finite, of course, that's the kind of thing, but you get fewer kind of, from these kind of congruence subgroups, you get fewer kind of subgroups of finite index, so that they define a slightly different topology. And if these two things agree, then we say we have the congruent subgroup property. And for this, what I want to state, we want it in the strong form, so the so-called congruence kernel is supposed to be trivial, and the strong form, that the congruence kernel, whatever that is, C of gamma is trivial. Then we do get a description. Then we do get a description of the representation zeta function. So then we do have a group with polynomial representation growth. They're rigid, and we do get a description of this in terms of two paths. They are now to generate essentially representations. So this OS is ring of integers in some number field K. And so you see representations coming from embedding gamma into, let's say, SLN, into SLNC, and then looking at kind of representations, I mean, in the sense of algebraic groups, irreducible representations of SLNC. And these are very well understood. They are kind of classified in terms of highest weights. There's a theory that somehow, combinatorial theory, that gives you a description of these kind of irreducible representations. And okay, then there's a certain multiplicity here, so this is just this zeta function to some power, which is the degree of the number field over Q. So if we do SLNZ, we will just see kind of, in this case, we will just see the SLNC. We'll just see the irreducible representations coming from the algebraic group SLN. This is called the Witten zeta function, kind of sometimes. Witten zeta. Okay, this is relatively well understood. This is from the Archimedean primes. And then there's something that, well, we like to call an Euler product. So now you run over all primes of this ring of integers. And well, we've inverted S, so we take things that are not in S. And then you get these local zeta functions. And these are the ones for, and now I will cheat. So maybe I should have put a box here. I will cheat a little bit. So you see basically the group, but evaluated at the completion, so at P. So this is like the p-adic completion of my arithmetic group that I had to start with. Okay, and in finitely many factors, you will see something slightly different than what I wrote down. I mean, you have to choose some kind of embedding, and then, I mean, to make sense of these symbols, G of, I mean, we should sort of define better what I mean by this symbol G underlined, some kind of scheme, right? And so, but in principle, this is more or less what you see. And in our examples, maybe this is the most kind of precise thing I can say in these lectures. You will see exactly this. Yeah? You will see these objects that, well, for the case n equals 2, were described here. Yeah? But n equals 2 is not good for the congruent subgroup property. So somehow this kind of kicks in when you start with SL3, or you've inverted at least one prime. So if you want to do SL2, you should do SL2 over Z invert 1 over, adjoin 1 over 3 or something like that. Okay, you can do that, yes. What do you mean by GC? These are the complex. This is this? Yes. Okay, this is this I didn't define. This is an algebraic group, simple algebraic group, and this is just the algebraic group. So viewed from a group theorist point of view, it's the C points. Sorry?
I mean, K doesn't, there's more than one K algebra structure on C.
So I take a simple algebraic group. It's defined over K. Well, it's defined over OS, really, or over O or something. But I take it defined over K. And that's fixed. I mean, with a fixed, and C is lying above it. Just take the solutions.
It's an embedding of K.
Yeah. Yeah, it doesn't matter. I mean, that's why you have this different ways of embedding it. Yes, that's why that multiplicity comes about. Maybe that's the question.
Yeah, so in particular, the signature of the number field doesn't play a role. You always get.
Yeah. This only depends on the, I mean, on the absolute kind of type of the Chevalier type of your group. Yeah. I don't need to do this for R also separately. That's right. Yeah. I don't have to distinguish between real embeddings or complex embeddings or something like this. I don't. Sorry, this maybe you're a bit quick. How are we doing? Okay, 5 more minutes. Okay. So
Actually, Benjamin, take 10 more minutes.
Take 10 more minutes. Okay. Okay, good. Thank you. Okay, so maybe I can come back to that. Picture. Okay, I forgot to say. So, I mean, yeah, this uses high power machinery. So this uses Margulis superrigidity. So this uses my rule is super rigidity. So so you still have something to do, but somehow it uses high-powered machinery. So it's not like you prove it from scratch. Okay, so maybe since I got 10 more minutes, yeah, maybe I can say something, like, at least in this, okay, in this example, let's just sort of indicate briefly how this comes about. I mean, I cannot sketch a proof, but how this comes about is, okay, you take your group gamma, so in my case, this is SL and Z, and I mean, there are two things you can do. You can embed it into SL and C, and there's a fixed embedding of Z into C, and there's nothing to discuss. Or you can embed it into SL and ZP for any prime P. And here we will be p-adically dense. I mean, in the p-adic topology, this will be a dense embedding. And this is a Zariski dense embedding. I mean, it doesn't look dense at all, but in the Zariski sense, this is a Zariski dense embedding. And so what I can do is I can take anything, from this, I can, of course, map onto SL and Z modulo P to the KZ. So this is like the same. I could have gone here directly, like for every K, but somehow this is a way to string things together. And so from these groups, I mean, the representation theory of this group I understand very well, as I sort of said before. The representation theory of this I don't understand so well, because this is not a field, this is a local ring, a finite local ring. But at least there is this Deligne-Lustig theory that sort of tells me what happens for K equals 1. And so I take representations rho into, well, GL and C irreducible from these groups. So I have a supply, I imagine I have a supply from these, and I certainly have a supply from these. Because of these dense embeddings, that means that they will also be irreducible, viewed as representations of SL and Z. Yeah? So I will produce irreducible representations in this sense. And now this black box tells you that the only thing you can do afterwards, in some sense, is you can form tensor products. If you do a tensor product of two irreducible representation, you get another irreducible representation. And that is encoded in this kind of product here, and the product here. Yeah, so this is the supply of the Lego blocks, and you can tensor them to get basically this expression for the zeta function. And if I was to do this over a number field, then we would have different embeddings. These are your different embeddings, and that's where this kind of extra factors come from. Okay, so that in a nutshell is sort of what's going on. And the big mystery is this part, yeah? Sort of from here via these different Ks, there's some choice of K, to here. This is not understood. This is not well understood. And our idea in some sense is that, well, we are not going to try and understand it completely, but we're just going to say something about the distribution of these irreducible representations by looking at the zeta function. Okay, that's the basic idea. Okay, and there's some machinery. So what happens when this, does anything explode, or does it sort of? Okay.
This doesn't explode.
Okay, good, okay. Good, okay, good. So there's something, again, I cannot explain in great detail, but I can indicate. So there's something called the Kirillov orbit method. It started kind of for real kind of unipotent Lie groups. Then, I mean, how kind of generalized it to kind of nilpotent groups in some sense, but also in this kind of p-adic setting, there's this kind of method. And it gives you a handle on exactly what we're interested in, the kind of dimensions of irreducible representations of these p-adic groups. And how does that work? So when we have this Lie correspondence, and imagine now we're interested in this group. So let's first treat this group down here, which is a bit easier to understand. Then we have this Lie lattice, and there's an adjoint action. So somehow this comes equipped with an adjoint action. So there's the Lie lattice, and this comes adjoined with an adjoint action of my original group. Now it's called U, okay? And we can look at the Pontryagin dual of this Lie lattice. So just look at it as an abelian group, and look at it as an abelian group. Okay, I have 10 more minutes. So the Pontryagin dual of this, let me denote it by that, is just to give an indication. I'm not going to develop the theory. So you look at all the continuous kind of functionals. So you look at your abelian group, underlying abelian group, forget the Lie bracket, and you look at the character, so to speak, so the homomorphisms into C star. So it's like the character group of this abelian group, but continuous. Okay? And now there's an induced action here, because these are functions on here. So if you have an action on U, you get an action on here. This is called the co-adjoint action. And I don't know whether there's a symbol for this. Let me also denote this by add. There's a co-adjoint action. Okay, let me denote this by add tilde, just to be sure, but this is the co-adjoint action. Maybe I put the tilde here. Okay, and now what are characters? So we are interested in another way to write this zeta function. So the zeta function I'm interested in for my group, now it's called U. Okay. For my group U, I can also, the irreducible representations, they correspond to characters. Every irreducible representation is uniquely determined by its characters. You just take the trace of the matrices. And the dimension is just the character evaluated at 1 to the minus s. So this is another form to write our thing. The question is, how do we get our hands onto characters? So characters are maps from U to C. That's what you get when you take traces of complex kind of matrices. They are maps from U to C. So here we have maps from this Lie lattice U into C star. But as I said, Lie lattice U is the same as the group U, so we already have maps from U to C, even to U to C star. There's some maps from U to C star. So out of these, we can somehow build the characters, the irreducible characters. And the way to do that is to look at the orbits under this action. The orbit, I mean, this is a discrete group, and this is a profinite group, so the orbits are finite. And so you take the average in some sense, the weighted average over each orbit to get sort of your character. So somehow you find there's a bijection between these, I have U instead of G, between these, this Pontryagin dual, so these functions from U into C, modulo the action of, the co-adjoint action of U to the irreducible characters of U. And the way it works is, so you take an orbit, so it's represented, let's say, by omega at U. This is a finite, this happens to be finite. It's an orbit, and you map it to the sum. You just sum over all the elements in that orbit, all omega tildes in this finite orbit, omega at U, and you evaluate omega tilde, well, at the group element that you're interested in. So this should be a function, that sends little x to some value in C. And well, you go with the x, you go back with x, you go with log over here, then you can evaluate, then you go with x. So you can write it in various ways. So let me just write it like this. You take, let me just write log of x. Yeah, this is a group element, so I move it over. It's the same element if I construct my Lie lattice like that and apply my functional. I do this across all the things in my orbit, and then I get a function from my group to the complex numbers. It was, the summons were in C star, but when I sum them, I might get 0, it could happen. But now I also need to normalize, so there's a normalization, and it turns out that you take the length of this orbit, and the length of the orbit, it turns out, is a square, so you can extract the square root. So that's technical. So this is magically, in some sense, this resolves the problem that we know from finite group theory, that the number of irreducible characters is the same as the number of conjugacy classes, but we have no bijection. So here we have a bijection. It's bijection between irreducible characters, not the conjugacy classes in U, but these kind of coadjoint orbits. Yeah, so in some sense, it solves this kind of problem that is sort of, that is there in general that we don't know how to solve in general. Okay, so now I think I will finish with, am I allowed one more board? There's many more things. So this is now, I mean, so we now got up to 2008 or 2010, something like that. So there's now a lot of people who have worked on these things since then. So let me just sort of finish with one table. Maybe one theorem and then one table. So if you do all this work, you get the following theorem. So this is an intermediate theorem, but I think this sums up what I was trying to say very well. So this is already in Heiken-Sapiran's paper. You get the formula for, so if G is a fab, so you can write down the zeta functions, the fab group, and you're uniformly powerful, so you have a nice Lie theory pro P group. Then you can look at the, so this is what I called U before, now I call it G. You can look at the associated Lie lattice G, then the representation zeta function of this uniform pro P group is equal to the sum over all elements in this Pontryagin dual. So that is, this is a very nice thing. I mean, this looks complicated, but it's a very nice thing. I mean, there's a free abelian group, so you just, it's a very nice thing. And you look at the index. So this now looks a bit like subgroup growth again. So we look at the index of what's called the radical of omega. So I'm not going to define what it is, but you can ask me afterwards. And you raise this is a finite index kind of subgroup. And so you raise this to the power -1/2 times s plus 2. Okay, so your task is now, so you now have something that's very well understood. It's an infinite, but sort of it's well understood summation set. You have the task to kind of evaluate what are these radicals and figure out what is the index. So in some sense, a bit like subgroup growth. And then you raise it to some shifted version of S. I mean, instead of S, you put 1/2 S plus 2. And this 1/2, and so it takes care of what we did here. There's some kind of overcounting. So this is the algebraic formula that sort of then is the beginning of some kind of coherent theory. Okay, and so what remains to do if you're interested in, let's say, the zeta function for SLNZ are two things. So one is, I mean, you have to work this out in some sense. You can then, Heiken shows this is again a rational function somehow. But the crucial thing is you have to do this uniformly across all primes, yeah? Or all primes here maybe. Uniformly across all primes, because there's no good, this is an infinite product, so you need to control these factors in some uniform way across all primes. So this machinery helps to do that. And here it says SLN, this is not a uniform group. I mean, there's this finite gap, and infinitely often there's a finite gap, so you still need to bridge this gap. This is something I haven't talked about at all. So, but it's really crucial you do it because the product is an infinite product. So you cannot avoid, you could avoid finitely many finite gaps, but not infinitely many. So you need to bridge that. And if you do that, then somehow you can, okay, this is comparatively well understood. You can sort of try to say something about this, the zeta function, or at least maybe the alpha. And so I will finish with a table. Short table. So this is, now look, going back to a very special example, this is a table of alpha G, so I'm now going back locally. So globally might be a different matter. We don't quite know how to do this Euler product. So we do this for the group alpha G for G SL, and now it doesn't matter because it's a, I can write one or not, it's a commensurability invariant, and I want to write this in terms of n. So how does this relate to n? So if n is equal to 2, we have this explicit formula, and we discovered that this alpha is 1. This was Heiken's result. For SL3, it took us a long time to figure out, but we figured it out. So it's 2/3. So this is the joint work with Avni and Uri and Christopher. SL4, this is something that Michele did, and I think he got 1/2. And up to this point, it all looks like 2/n. But this result of Larsen and Lubotsky, I didn't write it, maybe. Okay, Larsen and Lubotsky in this paper, they have another result, very surprising result, which says that, I mean, for general n, this should always be bounded away from 0, so it should be at least 2/11 in this case. Yeah, it's very strange. So this looks like it goes to 0 as n goes to infinity, but somehow that's just sort of the beginning. So generally, this is bounded away from 2 to the 11. And another result by Avni and Eisenbart is that, okay, it's bounded above from 22, and this was improved actually to bounded above by 2 by Michele and Boudoir. So there's a kind of, there's now a very short, in some sense, a very short interval between 2/11 and 2, where somehow this sequence has to develop. And I don't know whether there have been any recent developments, but I guess not much is known. So this is another kind of mystery that needs to be solved, and I'm well over time, so thank you very much.